Okay, this is the P4 paper from January 2021. It's question number 7, and we can see this is an integration question. We're actually going to have integration by parts for that one, and then we're going to use that answer to find the area under a curve for the second part. Okay, let's have a look at this integration by parts because it's a very interesting one, and I'm going to do a little bit of teaching just before we get started with it, just to make sure that you're aware of the type of question that we've got here. So when we do integration by parts is normally when we've got some sort of product here, two different values, and typically we might have something like x cos x, x e to the x, something like that, where what you're going to do is allocate one of them to be u and one of them to be dv by dx, with the idea that when we do all our work, u will be differentiated and will get simpler, and dv by dx will be integrated, and so I don't want that to get more complicated. And that's why if I did have those two, I'd choose u and dv or u and dv, because of the properties. The integral of cos is just sine, the integral of e to the x is e to the x, so they're not getting more complicated. So with one of those, we could have x log x. That's one of the exceptions to the rule that when I'm trying to do this, I can't have this as being dv by dx because I don't know how to differentiate log x. So what I'd have to do in that case would be to call this one dv by dx and this one u. But it works out when we do that type. This is the third type then that doesn't come up very often. I don't think it's even in the textbook particularly, but certainly it comes up in exams, that when we're looking at this one, actually, if I decide to make this u and this dv by dx, when I apply the integration by parts, I won't get my integral getting simpler. And I'll show you how we're going to cope with that by actually doing the question rather than trying to make it too confusing to get going. But right, okay, so let's have a look at this question then. So if we've got this situation, what I'm going to do, and we'll see it as it actually develops from doing the integration by parts, is I'm going to say u is equal to e to the 2x and dv by dx is equal to sine x. So if I'm going to do that, differentiating du by dx is going to give me 2e to the 2x, and the integral of sine is minus cos x. And then with integration by parts, we use the idea that the integral of u dv by dx is equal to uv minus the integral of v du by dx. Well, let's substitute everything in then. So I'm going to get that the integral of e to the 2x sine x dx is going to be uv, which is these two, uv, so that's going to give me minus e to the 2x cos x minus the integral of, and it's always the bottom two when we're doing integration by parts here, so that's going to be 2e to the 2x cos x dx, and we say, right, okay, I was hoping that this would get simpler. It hasn't actually got any simpler, and what I will need to do now is I'm going to need to integrate this part here, but almost call that one now and say, let's integrate that. I'm going to need to do integration by parts again. Now, we're used to doing that, doing integration by parts twice here. Let's see what we're going to get with this. I'll just go through and actually do it all, because otherwise it's going to take me quite a long time to explain on this video. So I'm now trying to do the integral just of this bit. Okay, so if I'm going to do the integral of that bit, we're going to repeat the process. So we're going to say u is equal to 2e to the 2x, which means du by dx will be the differential of that, 4e to the 2x. We're going to say dv by dx is equal to cos x, and so v will be the integral of that, which in this case is sine x, and we're basically going to apply this thing again. And actually, I'm going to copy that down using the iPad. So copy that and put it as my next part here. Okay, so if I'm doing that again, I'm going to get that the integral of 2e to the 2x cos x dx then works out to be uv, which is 2e to the 2x sin x. You can do this a bit slower than me, minus the integral of 4e to the 2x sin x dx. And then at this stage you say, well, hang on, this hasn't got any simpler again either. But what has happened is we've got to a situation where we can now solve this. Let me show you how. So if we go back up to this line here, I'm now going to do that line. I'm going to replace this bit with all of that. So you can do that slowly. Let's have a go at me trying to do that then. So what we get is that our original question, the integral of e to the 2x sin x dx, is equal to, well, we had that uv from before, which was minus e to the 2x cos x. We had plus all of this bit now, so plus all of this bit here, so plus 2e to the 2x sin x, and then minus 4e to the 2x sin x, the integral. So you might think we haven't made any progress here, but as I said, right at the start, I knew we were going to get this. What's really nice is that I've got, in effect, the same term there. I've got e to the 2x and 4 lots of e to the 2x, or rather e to the 2x sin x, and 4 lots of e to the 2x sin x. So those two things can now be combined. So I knew this at the very, very start, before I even started this question. I've got enough experience to now be able to say, I knew I was going to end up with this stage. We can just take that over to the other side using algebra, okay? That's going to become 5e to the 2x sin x dx is equal to my e to the minus 2x cos x plus 2e to the 2x sin x. And then what I can do now is to say, or we should have had a plus c at some stage through my integration. I'm not sure where you want to put the plus c in, but really all the way down when we did our very first integral, so even up there we've got a plus c. As long as we remember to put it in at the very end here. What I actually wanted was e to the 2x. So if I actually wanted e to the 2x sin x dx, that's what I actually wanted there. It's just a fifth then of the other part. So it's a fifth of all of this bit plus the constant. We don't need to worry too much about the constant. The constant can change all the time. It has the capability of just adapting and becoming different constants here. So I have now found the integral of that because I didn't need to get to a stage where I'd have to integrate this part, simply because it can go over using some algebraic skills. So as I say, go back to the original question, I knew that right at this stage, once I had these sort of terms where you've got one of them, you just think, it's not obvious to me which one to make u and which one to make dv, because both of them don't get simpler when I differentiate, both of them don't get more complicated when I integrate it, and they stay at the same level when I differentiate it. That then leads to one of these questions. They don't come up very often, as I said, I don't see many of them in the book, but in the exams they're every now and then, so it's really, really important that you make sure you've seen this video and tell your friends to come and have a look at this one of all the integration by parts questions that we're going to do. Let's do the second part then, 5 marks to that. Second part just says, right, can we find the area bounded by the curve, the x-axis, and it's the same curve. So basically what I'm going to do now is I'm just going to integrate between 0 and, okay, they haven't told me that value yet. So I've got to find out what x1 is so I can then integrate between it. So let's find x1 first of all. So find x1, and that's going to be the curve equal to 0. And if the curve's equal to 0, well, e to the 2x can't equal to 0. Think about what e to the x looks like as a function. Never actually works out to be equal to 0, so neither does e to the 2x. So it's when sine x is equal to 0. So that means that x is going to be 0 or pi. Yeah, so there's 0, and now we know that that value there is pi. So I now know if I want to work out region R, area R is just going to be the integral between 0 and pi of e to the 2x sine x dx, but now we can use that part there in order to be able to work this out, and we're going to need it as an exact answer. So this works out to be a fifth e to the minus 2x cos x plus 2e to the 2x sine x, all between pi and 0, and it's a matter of just putting those values in now. So just put pi in and then put 0 in, so e to the minus 2 pi cos pi plus 2e to the 2 pi sine pi, minus putting the same thing but with 0 in, so e to the 0 cos 0 plus 2e to the 0 sine 0, and then when we're going through, just stick all the values in. You stick them into the calculation, you know what sine 0, cos pi, sine pi are. That works out to be a fifth, and we've got nothing for the first one, and we've got e to the 2 pi for the second one, and the other one will have 0 minus 1. They're relatively tidy, so that works out to be a fifth e to the 2 pi plus 1. Let's just go back and see, what does it say about the answer? Oh, perfect, okay. So it said show it's equal to that. I thought it might have said give it as an exact answer or anything else like that, but yeah, that's exactly what we've got there. I suppose we could write is e to the 2 pi plus 1 over 5. Actually, I'm going to criticise myself here. I should have looked at that and been working towards it rather than, luckily, obviously, I got all my algebra right, but it would have been sensible just to have had a quick look at what we're trying to prove while we're going through and doing it. Okay, hopefully that all makes sense.